Hello everyone, my name is Zhijian Ren and I'm from MIT Software and Micro Robotics Lab. Today I'm gonna introduce our recent work on high lift insect scale aerial robot, which is powered by low voltage and long endurance dielectric elastomer actuators. For some of you who have been attending Monday's section, you may have seen our labs feature robots. These are all powered by dielectric elastomer actuators, which we usually call DEAs. I will introduce later about how to fabricate them and how we have improved the fabrication. This work is already published on Advanced Materials, and fortunately, we were selected as that week's cover. I love this photo so much because it explains a lot about why we want to build this type of robots, like by inspirations that we want to learn from bees, and how we fabricate it. The background is the SEM image of carbon nanotubes that we are using for conductive electrodes. The robot basically has been improved in 3 directions. The first one is that we increase our robot's lift-to-weight ratio from our previous work, 2.2 to 3.7 for 20-layer DA and 4.3 for 6-layer DA, almost double the performance. We achieved this tremendous improvement by redesigning the robot's transmission, wings, and wing hinges based on our dynamic model. And since we improve our fabrication techniques, we are able to decrease each elastomer layer's thickness so that we can reduce the driving voltage from 1600 volts to about 500 volts. As the driving signal is a sinusoidal waveform, the value here is the peak voltage of the driving signal. The last improvement is that we demonstrate that our robot has a longer lifetime that can operate 2 million cycles intermittently, and furthermore continuously work for about 5 minutes at takeoff voltage without any performance degradation or thermal failure. Here intermittently means that we drive the robot for 30 seconds and then let it cool down for 30 seconds and then repeat it again until it reaches 2 million cycles. Previously, the DEA was very likely to fail after 0.5 million cycles, and the longest time it can work continuously is about 2 minutes. So it's another huge improvement, basically doubles or even triples the performance. The video here shows us that our robot achieves the longest hovering flight with the best performance among sub-gram aerial robots. It takes off in 0.5 seconds and then hovers about 20 seconds. The maximum position error is 2.5 centimeters, and the maximum altitude error is 2 degrees. Of course, we implement feedback control to achieve this stable flight, and it actually implies that our DEAs are quite reliable with varied driving signals. Now I'm gonna briefly introduce our fabrication procedures, and we'll emphasize on what we have improved. There are 4 high-level fabrication procedures that start from constructing the elastomer electrode multi-layers, then cut and remove them from the substrate. Next, we roll them into cylinder-like actuators and attach electrical connections. And finally, install them into the airframe together with transmissions, wing hinges, and wings. Only the first step is related to reduce the elastomer thickness and achieve more layers. So I will focus on that. In the process of layering, we add an extra baking step after transferring CNT to reduce the elastomer curing time. Besides, we add a vacuuming step after spin coating the elastomer to remove the bubbles in the elastomer and make the elastomer layer uniform on the thickness. This will significantly improve the DEA stability and make it unlikely to fail with voltage breakdown. So previously, we repeat 3 steps: transfer CNTs, spin coating, and thermal curing, 3 steps. But now we repeat 5 steps: transfer CNT as usual, thermal curing for a while, spin coating as before, and then put it into vacuum for 2 minutes, and finally do a second round baking after a vacuuming process, 5 steps. After repeating for 20 cycles, if we want to fabricate 20-layer DA, we cut and roll the strip into a cylinder, connect the tether wire on two ends for power supply, and finally install it into the airframe. After making our 4 individual units, we can establish them into a flapping wing micro robot. We not only fabricate 6 and 20-layer DAs, we also fabricate 8, 10, 12, and 16-layer DAs to verify the improvement of our fabrication techniques. Under the same driving electric field, they exhibit quite similar mechanical performance. The driving voltage decreases with the layer numbers, so we use the voltage over layer thickness to make the comparison. The result implies that if the 6-layer DA works properly with the transmissions, wing hinges, and wings, all different layer DAs will also operate at a similar corresponding driving voltages. We don't worry about redesigning all these rigid components to make the robot fly. Meanwhile, we also characterize the driving current, the P2P value of the current for different DAs. It is an anticipated result that with voltage drops, the current will increase. Despite the current, we further investigate the electrical property of our DAs. Theoretically, the capacitance of DA is proportional to the square of layer numbers, while the resistance of DA is inversely proportional to the layer numbers. Practically, we calculate the resistance and the capacitance from measuring applied voltage and the current. As shown in the plot, the measurement aligns with the prediction very well. In addition to that, we calculate the input electrical power and see if it is close to the estimation. We find that the power consumption is approximately proportional to the DA layer number, which implies that the efficiency of DA decreases with its driving voltage. We then need to think about how to increase the efficiency while keeping the same performance. It will be one of our essential future work. In my first slide, I say we almost double the lift to weight ratio. Some of you may have questions how we measure the lift force, since it is usually difficult to get accurate measurement. In our case, we mount the robot on a balance beam that can rotate with respect to a pivot point almost frictionlessly. And we attach some dummy load on the end of the beam close to the robot. Then if the robot can take off and not rapidly go up, we are able to estimate the lift force by applying balance equation. For example, the 167 milligram robot can take off with a 400 milligram dummy load, but with only a few degrees rising. Then we know the lift force just balance the robot's own weight together with the dummy weight. The calculated lift to weight ratio is about 3.7. As you can see in both videos, we try different driving voltage and estimate the lift force. I mean, we can't say our measurement is quite accurate, but at least it is quite convenient for us to compare the lift force with different layer DAs. And from the plot, we can see that 6-layer DA has better performance than the 20-layer DA. It implies that the 20-layer DA's efficiency may be even worse, and we must find some solutions to that. But still, it achieves an outstanding lift-to-weight ratio of 3.7 that is promising for untethered flight in the future. Okay, not much time left, so I will just play the flight video again and show you some snapshots of the flight, also along with some tracked measurements of position and altitude to prove that it is really a decent flight. I mean, we are very glad that our robots achieves it. Thank you for listening, and I'm happy to answer questions.